Hi, welcome to the Introstat lecture series. This is the final exam review. This is the part 2 of the review. For the first video, we covered the 12 problems, and so from here we're going to start at number 13 here. Okay, so now let's go ahead to our exam reviews here. Okay, like we did for the problem number 12. So now let's go ahead to start number 13 here. All right, so the 13th here, the first problem here, number 13 is telling us the following partially completed two-way tables show the marginal distribution of gender and handedness for a sample of high school students. And the key word here is if there is no associations, okay? If there's no associations between the genders and the handedness for the member of the sample, what is the total number of the student will be right-handed in the female. Okay, if we are said this is the marginal distribution for the genders, right? So it's male and the female. If they're if you are right-handed or left-handed, if these two are independent, that means we're going to see roughly the same percentage of right-handed students for the male and the female student. The same way for the left-handed the percentage of student for the male and the females, right? Okay, so now that's what is the no association mean. That means if these two, the male and the female and the right and the left, if these two has no association, that means under the male, percent of the right-handed, and under the female, percent of the right-handed, they should be very close, right? So the same for the male, for the percent of left-handed should be very close to the percent of the female very-handed, right? The female left-handed, right? So, okay, now for the 60 over 80. So for here, for the male, I have 60 students. Total, I sampled the 80s, right? So I sampled the 80s here, and then the 60s of them are right-handed. So I know the percent of here is 60 over 80. So it's 6 over 8, so it's 3/4. So I know this is 3/4, right? So that means 3/4 of the male student will be right-handed. And because we are doing the marginal for the gender, so if this 4/3, then the remaining here is what? This will be 1/4. Right, 3/4 here. So this remaining will be 1/4 because this is a marginal. So when you add them together, it should be 100%. Okay, so now let's take a look for the females here. We say because they are independent, no associations, right? So their percentage-wise should be very, very similar. So that means the female left-handed will be very similar to the male left-handed. So what is here? So should be very close to 1/4, right? Because here, this is the 1/4 here, right? Okay, so now we need to calculate. So if 15 female is only the 1/4 of the females, right? The 15 left-handed is only 1/4 of the female. So what is the total female students we have? The total female student will be the 15 divided by the 1/4, right? Because that's what we have here. We have 60 students. So I know I surveyed 60 students for the female. Am I right? Okay. And now, because here, also the same, because the male is 3/4 is right-handed. So I expect the female will be 3/4 as well. And the total female is 60. So what is the 3/4 of the 60? So will be 60 times the 3/4. What that will be? That will be 45 here. Right, so this will be 45 students. So we can calculate this one also. We saw the male, the left-handed is 1/4. So what what is the male students is left-handed, it will be 80 times 1/4, so will be what is 20, right? So this is 20. So if the problem asks you what is the male left-handed, it will be 20. What is a female right-handed is 45. What is a female left-handed is 15, right? So what is the problem ask us here is right-handed female. Right-handed female is what? It's a 45 here, so it should be 8 here, right? So we need to know how to look at a contingency table. So the key word here is no association. It's no association. That means the percentage-wise it should be very similar. So that means these two should be very similar. These two will be very similar. Similar in what sense? Percentage, right? Be very careful for that. Okay, let's take a look at number 14. Okay, so here, number 14 say power. All right, so power is what? Okay, so let's remember we talk about these things here. We always write it and before you look at the answer, so the answer will not bias, right? So the power, we say the definition power is, we say is correctly reject the H0 when the H0 is false. Okay, so let's take a look at which statement is the best. Okay, so let's say first one here, the probability is non-hypothesis is true and we not reject it. No, it's non-hypothesis false. So I know this one is not the correct one because they say non-hypothesis true. So based on our definition, it's non-hypothesis false. Okay, so the probability that a false non-hypothesis will be rejected. A false wrong hypothesis be rejected. Well, this is the match our statement. Okay, let's see what's wrong with C. The probability a true non-hypothesis it will be rejected. So here still is a true non-hypothesis, but non-hypothesis is false. So that's why it's not our definition. Okay, so let's take a look at these here. The probability that the alternative hypothesis is true. And we not reject the non-hypothesis here. So this is not true. So when the alternative hypothesis is true, so basically you will say the H0 is false, right? So when H0 is false, you are not rejected. It's not what we defined here. So this is not the power definition. Okay, so the part E is here, the probability we are not making the type 1 error. So that's not true because we know what the power is equal to what is 1 minus beta. What is the betas here? Beta is a type 2 error. Okay, so it's not the probability not making the type 1 errors here. Okay, let's take a look at number 15. All right, so the number 15 said, suppose, okay, so suppose that the device advised to increase cars gas mileage, but in the reality, it does not work. All right, so we test it on a small fleet of the car. So here they pretty nice. They say in reality it's not effective. And our data resolved a p-value is 0.004. What probability happens as a result? What probably happens as a result of this experiment? All right, so this is the one, so we kind of it's the kind of very confusing wording, right? So let's write it out. When we write it out, I think it will help. So H0, so we say is not effective, right? Okay, so when the H0 is not effective, so let's say suppose the device can increase the gas mileage, but in fact does not work. Okay, so they claim it's effective, but it's not effective, right? So what is this statement translated to? this statement translated to H0 is what? H0 is true. Okay, H0 is true. Okay, then we test on the fleet, and then they said, then I have come out with a p-value is 0.004. Okay, so for 0.004 is a very small p-value. So what is this one translate to? Because p-value, that means we reject H0. Okay, so now we got our answer. So when the H0 is true, we reject H0. Okay, so let's see what will be our answer. We correct the fail to reject. No, that's not what it says. We reject H0. We correctly reject H0. But the H0 is true. We reject H0. No, we did not. So when the H0 is true, we don't reject it, right? So this here, we reject H0, making a type 1 error. Okay, that's true because when H0 is true, we reject it. So if you combine these two statements, right? So that means it's H0 is true, and then we reject it, right? So we reject H0. So what is this one? This is also, we call this a type 1 error here, right? So now we know this one is we reject H0, making type 1. Okay, so the D is here, we reject H0, make type 2, so this is not true. So let's say we fail to reject. No, we did not fail to reject, we correct reject because p-value is very small here. So the correct answer is C. Okay, let's take a look at number 16 here. Number 16 here, it tells us for any given value, for any given alpha value, the right-hand side, the critical value of t-test is always less than the right-hand side of the critical value of the z-test. What the characteristics of t-test cause of this effect? This is a pretty good question here. Okay, so in here, let's take a look here, right? So first, let me draw a normal distribution. So this is my normal distribution. And then also, let me draw a t-distribution here. So for the t-distribution, when we talk about the t-distribution, we said the t-distribution is a distribution have a heavy tail than the normal. So, oops, yeah, let me draw my normal better here, get a little bit. Okay, so this is my normal distribution. Then we know the t-distribution when we talk about the t-test, right? So we said the t-distribution is have a heavier tails, right? So this is a t, and this is a z, right? They both have a kind of the bell shape. I shouldn't exaggerate that much. We said still is look pretty much like the bell shaped, but still have a kind of a tail. So it's have a heavier tail. That means that the tail of the T is above the Z here. Okay, so now let's say if the alpha value for given alpha values, right? So because the T distribution, the given alpha value, so if this is alpha, right? Because T has a little bit of, the T. So this point here, this is a T the critical, right? T the critical. Because T is heavier than the Z, so then the Z, the alpha value come over here, right? So this will be the Z, the critical values here. So we know the T's, because they have a heavy tail, so the alpha is go to right hand more. So the T is always greater than the Z. So what is the properties here? And so let's take a look here, which one is the correct one. So let's say since T distribution is more symmetric than the Z distribution, no, this is not true because T and the Z both are symmetric. Okay, since T distribution depends on the degrees of freedom and the Z does not, this is a correct statement, but it does not tell you why the critical value here is the t is greater than the critical value of the z here. Okay, so then they said since t has a light tail, now we know the t has a heavier tail. Okay, so that's why here we say since t distribution have a heavier tail than z distribution. What is wrong with the e? Since t distribution sigma is unknown, well, we don't know. We do know the sigma, the t distribution is. We do know what is the sigma. We just a very complicated form to calculate that, right? So that's not a true statement here. All right. So because of the t has a little bit heavier tail than the z's, right? So that means when you have a fixed alpha value, then we push the t critical further, further to the right here. Okay, number 17 is here. We say in testing a hypothesis of two population mean, all right? So we are testing what is the two population mean. If the t distribution is used, which assumption is, is required? Okay, so first one here, we said both population mean are to be the same. Let's take a look. No, we did not require that. We say we want to test it. The sample size has to be equal. No, we don't have it. And the standard deviation are not the same. We don't know. We can be the same, cannot be not the same. So we do not have that's not the requirement. So the only requirement will be the A. See here, the both population are normally distributed because this is the normally distributed data is the underlying assumption for the t distributions, right? So it's an A. So remember, right, we don't require the sample size because you can have N1, N2. We don't require the population means are the same. That's what we try to test, right? Okay, number 18 is here. Okay, so these ones here we talk about, we say a good data set should include all 5W. So sometimes the 5W is not missing. So, but the minima, what is the minima information we need? We need to what? We need to what and what and the who, right? So this is very important because the who is giving you the data. So the who this basically is the first columns, right? So this is like the different person, different invoice. Then what is those variables here, right? So whatever you measure for those people. So those are the two basic requirement to make a data set. Without any one of this, without who or without what, is not going to be a meaningful data set. Okay, now let's take a look at number 19. See here. So we said assume the cholesterol level of adult American woman can be described by a normal model with a mean of 170 and a standard deviation of 20. If a cholesterol level is lower than 150, it's categorized as a healthy level. What percent of the woman has the healthy cholesterol levels here? So like we say, we always like to draw the pictures, right? So here, the normal is 170. So we want to see it's 150. It's 150 is here. So we say less than, so it will be here, right? So really, so this is just we try to use the what? We try to use the TI-84 calculator, try to find the the probability. Let's go to our calculator and let's see here. All right, so now let's see here, clear that out. So let's see the second bars, and then you do the normal CDFs, right? And now what is the lower bound here? So lower bound is 150. And what is the upper bound here? Upper bound is to the e to the 9999999, right? So the I'm sorry, the lower bound is negatives, right? So in here you can just say negative 9999999. All right, and the upper bound is what? Is 150. Okay, so now the means here is 170, right? And what is the sigma here? The sigma is what? It's 20. Okay, so now let's take a look at what is the probability is less than 150. So it will be 15865. Okay, so it's 15865. All right, so let's go back layer. So it's 15865 here. So let's see, do we have the answer 156? So from the calculator, we're going to point 1568, 156. What? I don't remember that. So 15865. Okay, 15865 here. Okay, so it's 1586. So 158. So this is 15865. So you are rounding. So it will be 0.159. So what is the percent? We have a 15%, of 15.9% here. That's the healthy cholesterol level. Okay, now let's take a look at the number 20 here. It said with regarding to the previous cholesterol level, if a woman's at the top 15 of the cholesterol level, then the doctor will need to prescribe some cholesterol medicine. What is the highest cholesterol the woman can have without the medicine? Okay, so in here you draw a picture again. So this is 170, right? So we say the highest 15. That means from here to here, right? So this area, this is 15%, so it's a 0.15. Okay, so I am going to find out what is this values here, these green values here, right? Will give me the 0.15. That means if I don't exceed this green value, then I don't need to take the cholesterol medicine. Okay, now in here we know when we use our TI-84 calculator, we always see it's going to the left, right? So we're going to use what table? We're going to use the inverse norm. All right, let's see whether we got what do we have here. All right, let's go to our calculator. Let's do the calculator one more time. Here we go. All right, so clear this out. You do a second bar. Now we do the inverse norm is here. So the area, remember, right? So it's the left. So it's like the golden area we just said. So the red area is 0.15. So what is here? This will be 0.85, right? Okay, now my means here is 170. And my sigmas here is what? It's 20. All right, so let's take a look at what we have here. I got a 190.72. All right, so let's go back to our work, our practice exam. So we just did the calculator. So this one gave us is 190.72. Okay, so that's what the closest ones here is what 190. That means if you are under the 190 in your cholesterol level, you don't need to, you don't need to take the cholesterol medicines here. All right. So now let's take a look at number 21 here. Okay, so number 21 here, they tell you airline flies the same route on the same time each day. The flight time varies according to a normal distribution with mean equal to 48 minutes and unknown standard deviation. On 25% of the day, the flight takes more than an hour. Whoa. And what is the standard deviation of the distributions here? Okay, let's take a look for draw the picture. Remember, we always draw the pictures, right? So these ones here, they give you, let's say, hey, the means here is 45 minutes, right? Then they said only 25% of the day takes more than an hour. Hour is what 60 minutes is here, right? So that means take a more than, that means over here, more than, right? So what is the percentages here? This is 0.25, correct? And now I want to find what is the standard deviations here. Okay, so now let's, so we know like in here, the way we said we can do the z-scores, right? So we say here, okay, so I should do the graph here. So let me see if you translate this to a z-scores, 45 going to transfer to what? To 0. And this 60s, right? So this 60, this is what I call the z-score. So the z-score will be the 60 minus 45 and divided by what? Divided by this sigma we try to find. Because even you transfer to the z-score, this area still is what? This is still 0.25. Okay, so now I need to use the inverse known, but I still need this area, right? This area is what? This is 0.75. So when I use the inverse known, right? So I can use the inverse known to find the z. So here, let's go to our calculator. Okay, so here, stop here. Let's do here, okay. Okay, so clear here. Okay, so I said the second verse, then the inverse known. Okay, inverse known. So what is the area with that? We said 0.75. Correct? All right, because we transfer that to the z, so become mu equal to 0, sigma equal to 1. Oops, here, sigma equal to 1. And let's see what is the z value. We got a 0.674489. All right, so let's go back to our exam review. So I just find by using the inverse known, I got that this is z value is 0.6745, right? Okay, so that means this z values, right? So it's going to be equal to what? We just get it. It's 0.6745. Now I know 60 minus 45 equal to this, divide the sigma equal to the 6745, right? So now in here, this is just a little algebra. 60 minus 45 is 15. Sigma is equal to the 0.6745. Then you multiply sigma both sides, so it's 15 is equal to the 0.6745. You times the sigmas, right? So you multiply the sigma both sides, right? Try to solve it. It's kind of like in your algebra here. So now the sigma here, you just divide it by the 0.6745. Okay, 6745. All right, so the sigmas here will just be 15 divided by the 0.6745. And if you, oh, I'm sorry, this is not a 15. I'm sorry, this is a 48. Huh? Right, so this is a 48. This is a 48. So this is 12. Okay, so let's make sure we correct this. So this is 48, so this is 12, this is 12. So this is 12 over 0.6745. And then you get the sigma is equal to 17.79. All right, let's take a look at which one is the closest one. Here we got this is the closest one, 17.8 here. All right, okay, let's take a look the another ones here. All right, so let's take a look at number 22 here. So let's say that on average, do women spend more time at a tanning salon each month than a man? research sampled 20 women and determined their mean to be 30 minutes. And the standard deviation is 5 minutes. From a sample of 25 men, the mean was determined to be 27 minutes with a standard deviation of 3 minutes. A test of the hypothesis was performed at a 5% level of significance. What is the pooled variance used for the hypothesis test, right? Assume the sample to take from the normal population with equal variances here, all right? So in here, what do we try to do here? We want to find we want to find the pool variances here, and we assume the normal populations. Okay, so for this type of the problem first, let's okay, so let's try to write down all the information here, right? So we say the woman, how many women we take? Okay, sample size is 20. What is the mean is here? Mean is 30 minutes, and what is standard deviation is 5. Then for the man, how many sample men we took? 25. What is the mean is 27, and the standard deviation is 3. Okay, now let's go back to our calculator. All right, so let's go back to our calculator here. So the calculators here, let's see here. All right, so let's clear out. So this is the two population t-test, right? So let's do a stat to do a test. So we say it's a two sample t-test. So in here, they give us the statistic. So we move the cursor here, statistic, hit enter. All right, now in here, the x1, okay, so the x1 is the woman's number, so it's 30. And the standard deviation for the x1 is 5. What is the sample size? Sample size is 20. Okay, so now for x2. Okay, so x2 is man. So the man, the average is 27. And the sigma is what is 3. And the n is what, 25 here. All right. Okay, so we want to test if the woman spend more time than men, right? So we say, okay, we want to test this. Okay, then in here is be careful here. So we want to find the pool because we assume they're taken from the population. So we want to go here, say, yes, I want a pool, right? Okay, so then in here you do a calculate. So they give you all this information. And then now take a look and what is the problem asked here. So they want to find the pool variances here, right? Okay, let's go down here. All right, so let's go down here. So here you say, oh, this is what we are looking for, right? This is the XP pool, right? So this is, this is what the, oops, here. So this is got the, okay, so SP is 4.0087, okay? Okay, so now let's go here. So from the TI-84 calculator, so what do we have here? So we got SP pool, this is 4.0087. But in here, what we are looking for here? We are looking for the pool variance. And what is this ones here? This is the pool, the standard deviation. Right, so the variance will just be the square. So it will be SP, the square. So it's a 4.0087 to the square. So it should be very close to 16ths, right? Okay, so here just be very careful. So what is the answers here? The answers here is 16ths here. All right, let's take a look at number 23 here. So we said a hypothesis test is done in which the alternative hypothesis is more than 10% of the population is left-handed. The p-value for the test is 0.14, which statement is correct. All right. Okay, so let's try to write it. Remember, we always, if we write it, so probably it will be better. So we say H0 is the proportion is equal to 0.1, and the alternative is here, we say the proportion is greater than 10%, right? And then with the p-value, this is the p-values here. The p-value is 0.14. So p-value is greater than 0.05. So what we do here, so we will reject, fail to reject, right? So it's, so we fail to reject. Fail to reject H0. Yeah, okay. So let's try to see which statement is true here, 23. We can conclude that more than 10% of the population is left-handed. No, we say we fail to reject, so we stayed here, right? So this is not true. We can conclude that more than 14% of the population, we don't know. No, that's not the mean value of the p-value mean. So here, we can conclude that exactly 14% of the population is left-handed. No. We cannot conclude that more than 10% of the population is left-handed. This will be the correct statement. Why? Because we failed to reject H0. That means we stayed here, right? That means we stayed here. So that's why we said H0. So that means we cannot support more than 10% is left-handed. All right. All right. So now let's take a look at number 24 here. Okay. So number 24, they talk about when you test for differences between the two population mean from the small samples. When should the pool variance is used? Okay, so we talk about the pool and the non-pool. Right, so we said things for the pool to be used. That means if we can assume these two populations has the same variance or same standard deviation. All right, so that's the pool variance conditions here. So that means we can assume the two populations have the same, similar, or very close, the same variances. Even we don't know what is that, right? Okay, so A, the two sample test is no, they can do one. When the sample size are different, no, we don't, that's not the criteria we use to decide whether we're going to use a pool or not. So they say always calculate the pool. No, that's not what we say, always calculate the pool. So the D say when the population variance are assumed to be equal, this is what is the condition for the pool. We assume these two populations have the same variances here, right? Let's see what is wrong with E. When the population variance is unknown, okay, both this is unknown, but one is assumed to be equal. It's unknown, but in here the reason why this one's here, let's say, is assumed to be different. If you assume to be different, then what do you need to use here? You're going to, because if you assume to be a different, you're going to use not a pool. Right, so the answer is D here. All right, let's take a look at number 25 here. All right, so number 25 says, when we will test the hypothesis that mu is equal to 25 versus H mu is greater than 25. We don't know it, but actual mu is 28. With which of the sampling and the significance level our test have the greatest power? Okay, so let's take a look here. Let's write it. This is the H0 mu equal to 25, and the HA is mu is greater than 25. So okay, let's try to highlight the information. So let's say actual mu is 28. So that means actually, so this is in here, right? So this statement give us is what? So H0 is false, right? So this ones here give us H0 is false. And so we want to the greatest power, the power is H0 is false, and we correctly reject H0. All right, so correctly reject H0. What's that mean? That means, the correct reject H0s, right? So we support the H0, HAs here. So H0 is false. Okay, so let's take a look here. So the first things here we know. Okay, so we know the greater the sample size always give us the highest powers, right? So we can cross out, right? So we can cross out the A, we can cross out the C. So now the alpha is 0.01, n equal to 500, and alpha equal to the 0.05, n is equal to the 500 here. So which one will give us a correctly reject, given this is the powers, right? We want this one, the powers is the greatest power. Okay, so we know if I have my alpha value is smaller. Remember this thing we talk about when the alpha value is smaller, then the beta value getting what? Getting big. If getting big, right? So if then the 1 minus beta, what is this ones here? This is a power. It's going to get smaller, right? So on the other side, if your alpha value is a little bit is bigger, then beta value is smaller. If beta value is smaller, 1 minus beta is power going to be what? Going to be, this is the power, right? Going to be bigger. So I want to choose the alpha value equal to the what? 0.05 here, right? So this one will be the D's here. Okay, and so for this video, let's stop here, and then we will continue to work our next video for the remaining problems here. All right, have a good day. All right, and study hard and get a good grade. Okay, talk to you later. Okay, bye.